Once again, welcome to today's webinar focused on oil and gas industry applications. This is the fourth and final one of the webinar series we are having this year. And in the past, we covered packer seals, centralizers, and pipeline inspection devices. And these webcasts are available on our website, and you are welcome to download them if you did not get a chance to attend. Today, we are going to look at the use of control systems in Drawworks. And with me today is Rick Clanton, who is in our support group and comes with extensive experience in analyzing complex control systems across several industries. MSC Software is the leading global provider of virtual product development tools, including simulation software and engineering services. We have been helping companies reduce product development costs and increase product innovation for over 45 years. Through a broad range of tools, solutions, and services. As we have been demonstrating through the webcasts, MSC solutions have applications in several segments of oil and gas industry. These include sealing systems, including packer seals and blowout preventers, bottom hole assemblies involving contact and wear and tear studies, offshore structural analysis, safety of storage and pipeline structures, control system efficiency, turbo machinery stability and safety, and the pipeline devices used to maintain and monitor the pipelines. So with that brief introduction, let us now move on to the central topic of this webcast. After a brief review of the control systems and their design challenges, Rick will introduce MSC simulation solution for these applications and then go over an example. We will then briefly talk about MSC solution to manage the simulation data and then have a Q&A to address any questions you may have on today's presentation. Control systems have a very critical role in the industry during exploration, drilling, production, and maintenance phases. The goal of these systems is to improve the performance of the mechanical systems while eliminating or reducing risk associated with the operations. These risks may be associated with human injury and discomfort or damage and failure to the mechanical systems. So because of the complexity and safety requirements, there are several operational parameters and systems that need to be controlled. So these include the pressure, temperature, and flow, operational speed of drilling, loads, mud circulation, blowout prevention, noise and vibration of the systems, and corrosion, to name just a few. So there are different possible strategies to implement controllers used during the drilling stage of operations. These include open loop controls, where the system is controlled directly only through input signal, or a closed loop control where feedback is used to obtain better control of the system. The controls could also range from simple PID controller to PLC automated controllers. A PID controller could be used to improve the signal rise time and overshoot, and also to reduce the steady state error. PLCs, or programmable logic controllers, are used to monitor and maintain multiple input and output arrangements. So PLCs also form the basic components of more complex DCS control systems as well. So all these controllers, of course, may be based on electronic components, while several are also based on hydraulic, pneumatic, mechanical components, or any combination of those. So control systems in oil and gas industry have unique requirements because of the broad set of constraints they need to be designed for. In addition to engineering and safety requirements and operational efficiency goals, they also need to be designed to satisfy government regulations while addressing any environmental issues. Some of the challenges include the extreme environmental conditions that these systems need to withstand in terms of pressure, temperature, corrosive environment, and so on. Safety also plays a key role, since any damage and failure of the systems need to be avoided. Also, for the sake of efficiency and resource conservation, circulation of fluids also need to be controlled as well. So with such broad set of constraints, it is very important for designers to make sure that they have an optimal system possible while meeting the cost and time goals that they need to operate under. So at this time, I would like to turn over to Rick to talk about our control solutions and how our users can benefit from the use of the multidisciplinary solution that we offer.
Thanks, Srinivas. So first, let's talk about what EZ5 is in case you're not familiar with it. It's an advanced multi-domain simulation and design tool. It can model multiple types of systems across a wide range of mechanical disciplines, including mechanical, hydraulic, pneumatic, thermal, powertrain, environmental and motion controls. The list goes on. It has the capability to have customizable libraries of components so that engineers can tailor the software to their specific applications and requirements. It offers a complete system virtual simulation by linking to other CAE programs and MSC applications. EZ5 has been very integral in many of the industrial and heavy machinery type companies. Here's a partial list of the systems and applications that were simulated using EZ5. There are hydraulic systems, climate control systems, power generation, off-highway and rail vehicles, and of course, oil drilling and exploration equipment. So here are some highlights of EZ5. It has powerful and robust simulation capabilities for systems analysis. You model your system by connecting up pre-built system-level blocks. You can integrate your EZ5 model with other CAE tools for multidisciplinary solutions, and it has extensive customization capabilities. EZ5 also has powerful simulation capabilities. You can do steady-state analysis, linear model generation and analysis, stability analysis, and of course nonlinear analysis. It can easily handle nonlinearities such as backlash, hysteresis, stiction, cavitation, water hammer, phase change, turbulent transitions, etc. EZ5 has 8 application libraries available. These libraries group hundreds of system-level blocks which have embedded in them predefined models developed by experts. These libraries model a broad array of systems, namely thermal hydraulics, engine systems, powertrains, aerospace vehicles, gas dynamics, electric systems, fuel cell systems, multi-phase fluid systems, so on. These are used in many industries like transportation, aerospace, off-highway equipment, defense, biomedical, power generation, the list goes on. Most of these products in these industries involve one or more of the above systems. With these libraries, you are at an advantage in that you can quickly put together schematic models of those specific types of systems by building at the system level with pre-built components. For example, if your system contains a hydraulic actuator and a rack and pinion, the physics of those are modeled with their corresponding components from the EZ5 libraries. Here's an example of how EZ5 integrates with atoms to offer a complete simulation solution. In this example, the hydraulic and electrical control system was developed in EZ5 to simulate the special type motor in the flap. The higher fidelity multi-body dynamic mechanical model of the flap was done in atoms. This results in an overall higher fidelity model of the combined system. This enables you to deduce valuable information and get deeper insight into your overall combined system. Let's take a look at a case study from the oil drilling and exploration industry. Kverner used EZ5 in its thermal hydraulic library to model the undersea hydraulic control actuator lying on the sea floor. They were able to then predict its performance and the effect of the expansion and contraction of the 20-kilometer long hydraulic elastic hose running to it. The use of the EZ5 hydraulic library saved time and money because the library provided ready-to-use components. As a result, the customer didn't have to write a single line of code. Now I'm going to show you an example of EZ5, and Adams actually, simulating a system in the oil and gas industry. Let's look at the Drawworks operation that lowers drilling pipe down into the hole. A central pulley picks up a pipe and lifts it into place above the well opening. The pipe is held by a steel wire and is then let go, still attached to the wire, and then the pipe travels down the well because of gravity. Once the pipe gets close to the top of the pipe that's already in there, the braking mechanism, which is part of the control system, is engaged to stop it. It stops the pipe as close as possible to the top of the pipe already in the well without impacting it. The pipe is then released from the wire and joined to the one that's in the well. This operation is done as quickly as possible, but if it's not done correctly, the pipes could hit each other and get damaged. And if this happened, the pipe that was already in the hole and the one that was just introduced to the hole would need to be removed and replaced. Being able to stop a pipe that is going down the well at the desired position that you want is a difficult task because of the weight of the pipe from gravity. The Drawworks controller and algorithms need to be complex enough to account for the elasticity of the steel wires, the flexibility of the supports, the friction on the pulleys and the drum, the braking mechanism and its response, and the transmission of signals from sensors to the controller. The complete process of running pipe down the hole can be modeled with a combination of a multi-body dynamics tool, in this case Adams, and a control system tool, in this case EZ5. The Adams model includes such attributes as a flexible steel wire, the pulley and drum braking system, and the pipes going down the hole, and the derrick itself. The EZ5 model includes the hydraulic system, which takes into account fluid compressibility, component dynamics, and it also includes a proportional directional control valve, a pump, an actuator, and a reservoir. The EZ5 model also includes a simplified open-loop control algorithm. While it's simplistic, it nonetheless demonstrates the capability of EZ5 in evaluating more extensive algorithms. Here's a picture of the Adams model. You see the derrick with a pulley on top guiding the wire attached to the red pipe going down the hole. The lower portion of the wire next to the pipe is modeled as flexible wire. The other end of the cable is wrapped around the braking drum. The hydraulic brake is shown on top of the drum. The hydraulic system pressure exerts the braking force on the drum, thereby slowing the pipe's descent into the hole. The hydraulic system and the controls algorithm both are modeled in EZ5. The two software packages communicate with each other at a predefined interval, exchanging the results of their respective calculations. This is called co-simulation. So here's an animation of the Adams model lowering the pipe into the hole. The braking force initially is high to hold the pipe stationary. It's then reduced to allow the pipe to drop into the hole, and then the braking force is again applied to stop the pipe. This is a simulation showing what we don't want to happen, where the pipe that's being lowered down into the hole actually crashes into the pipe that's already in the hole. So if you wanted to investigate the effects of, let's say, a parameter variation in the Adams model alone, you could certainly do that. Here is the results of two different cable damping values on the simulation. You can see here what happens when the damping is reduced. Basically, the oscillation amplitude increases. Here's a picture of the EZ5 model schematic that's modeling the hydraulics and the controls. There's a constant displacement pump that is outputting continuous flow into the system. The max system pressure is governed by the system relief valve. There's also a three-way proportional directional control valve that communicates the pressure to the actuator, which provides the braking force. This hydraulics force from the actuator is communicated to the Adams model and provides the braking force on the drum. When the valve is shifted to the other position than what is shown in the schematic, the pressure in the actuator is then vented to tank, thereby reducing the resulting braking force. Here, the valve is commanded by a simple lookup table that's acting as a function generator. The command input is then run through a second-order transfer function to simulate the valve's mechanical dynamics, as well as the magnetic and electrical dynamics of the solenoid and current servo. Here, we assumed that the valve had a natural frequency of 20 Hz and a damping ratio of 0.7. The output of the transfer function is the actual valve spool position. So the spool position then determines the metering area of the valve. In this case, a simple linear metering curve was used in the valve. The fluid used here is SAE 30 weight oil at 20 degrees C. Fluid compressibility is included. We neglected heat transfer in this case, but could have easily included it in the analysis if we'd wanted to. As for the actuator, seal friction was neglected. Piston mass was included, but since the piston stroke is minimal, its inertial dynamics impacts the simulation only negligibly. Since we are mostly interested in the fluid control part of the hydraulic circuit, the dynamic response characteristics of the system relief valve is not that important. Therefore, the relief has a first-order time constant set to 10 milliseconds in order to not adversely affect the system response as a whole. So here are the results of the EZ5 model. From 0 to 1 second, the valve directs fluid to the brake to hold the pipe stationary. Now, 1 second, the valve is switched and the pressure is released to remove the brake. The pipe then begins its free fall into the hole. So at 3 seconds, the valve is switched on again, and pressure is again directed to the actuator to slow the drum and pipe down until they eventually stop. In this case, a valve command of 1 permits fluid into the actuator, turning the brake on, and a valve command of -1 dumps the actuator fluid to tank, thereby releasing the brake. Now here's the same plot as before, except that the act of engaging the brake to stop the pipe has been focused on and is zoomed in on here. The solid blue line is the valve command from the lookup table. The actual valve spool movement is shown as the dotted black line. The resulting fluid flow through the valve to the actuator is shown as the dashed red line. Finally, the actuator hydraulic force is shown as the green line. This directly corresponds to the pressure in the actuator chamber. So looking at this, it's easy to see the progression in time of the different dynamic events in the process. It's also easy to evaluate the contribution of, say, the valve dynamics to the overall event duration as compared to the contribution of the building of pressure from the flow in the hydraulics. Now, if you wanted to further evaluate the design parameters on the EZ5 side and their influence on the system, it is, like it was in Adams, easy to do so. Here, we've changed the relief valve setting in order to up the max system working pressure from 200 to 300 bar. Simulation results for the two system pressures are shown here. The valve command, again the blue line, is the same for both instances, as is the valve position response, in this case the blue-green line. This is because flow forces and pressure forces within the valve were neglected in this case, but you could add those if you wanted. However, you can see the resulting larger flow magnitude and duration when the system pressure was increased. The dotted bright green line is the flow at the higher pressure, while the dashed red line is the flow at the lower pressure. So here's the overall system response to the nominal 200 bar case. The valve command is shown, as well as the resulting braking force on the drum. The pipe or tube position is shown next, as well as its velocity. You can see that while the brake was actuated at 3 seconds, the pipe continued to travel down the hole for another 1.2 seconds or so before it came to a stop. Furthermore, you can also see the approximate 7 Hz oscillation from the cable compliance showing up in the pipe velocity curve. So here's the system response I just showed you, but it's been compared to the system response at the higher pressure setting. You can see the resulting actuator force increases from 22 kilonewtons, which is the solid blue line, to about 33 kilonewtons, the dotted black line. This results in the pipe being stopped sooner, having traveled only about 5 meters, the bright red line, versus the 6 meters of the lower pressure run, the dark red line. However, you can also see that the magnitude of the velocity oscillation, which is the really light orange line there, also increased in magnitude when we upped the higher pressure. What was just presented was an open loop controller where we simply told the brake when to engage. This was done just to demonstrate the simulation capabilities as well as the possibilities for investigating system parameters. But the obvious next step would be to introduce a closed loop controller on the mechanism. One could feed back any number of variables into the controller, and then that would command the valve to apply the pressure. For example, you could feed back the pipe position from atoms into the controller. The controller would then command the valve as needed. That particular arrangement is shown in this EZ5 schematic here. There are numerous possibilities for further investigation regarding the system. First, you could try increasing the model fidelity and accuracy by introducing more complex physics into it. Possible additions include modeling internal valve components and behavior, such as pressure forces, spool friction, flow forces, detailed solenoid dynamics, etc. You could model the electronic hardware, including data sampling rates, control loop execution rates, and hardware and software filters, for example. You could model fluid line effects, such as pressure drops around bends, capacitance from hoses, internal pipe friction. You could evaluate friction effects from actuator seals, valve spools, brake pads of different materials, the pulleys, the drum, the pipe rubbing inside the casing in the hole, etc. You could evaluate temperature effects on the fluid viscosity and on the brake pad friction. You could also model the structure flexing, perhaps the derrick or the drum or pulleys, or also the entire length of the cable. You could then try different control strategies for the closed loop control, maybe a PID or even a nonlinear technique like fuzzy logic, for example. You could evaluate closing the loop on different parameters such as actuator pressure, which is directly related to braking force, maybe pipe position or velocity. Finally, the model would be an excellent resource to evaluate the sensitivities of certain system parameters like max system pressure, hydraulic component sizes and dynamic characteristics, structural flexibilities, temperature effects, and so on. With that, I hand the presentation back to Srinivas to discuss simulation management.
Thank you very much, Rick. While we have not shown all the complexities that can be handled by our solution, our goal here is to demonstrate the value our control solution brings to simulation of these complex systems. I would like to switch gears now and talk about another often ignored aspect of simulation, namely simulation management. Using simulation often creates a lot of valuable data. By that we mean any type of data relevant to simulation. It could be models or model configurations, your CAD/CAM files or CAE files, the results and material properties, and so on. If these massive amounts of data are not managed effectively, it could result in poor reuse and knowledge sharing, in addition to communication process inefficiencies within the company. So Sim Manager from MSC Software offers the possibility for everyone to collaborate and get their simulation work done better, faster, and more reliably. It is a web-centric framework for sharing, collaborating, and controlling your simulation data and processes. It is also easily extensible and customizable to meet your specific needs. Through this web-based platform, your simulation data will be securely available around the globe, version controlled, and secure role-based access control. In addition to providing simulation software, data and process management solutions, MSC also has a large services team placed across the world to assist our customers to quickly realize and enhance the value of their investments. By executing simulations or training your employees, or automating processes, or implementing web-based systems to manage and coordinate the simulation data, they can engage with their customers on many different levels. With that, let me summarize what we have covered in this webcast. So we have provided an overview of our control solution EZ5 and also demonstrated through a specific example on how it can be coupled with our dynamic solution, namely Adams. MSC strives to be a single source for your complete simulation needs, as demonstrated in this and the other webcasts that we have done. Once again, thank you very much for taking time to attend this webcast, and please stay online for question and answer session to follow.